This is Jim Hendershot with lecture number 32. The title of this lecture is PM Synchronous Generator Design Principles. Now, we've touched on a few aspects of generators before, but we're going to dedicate an entire lecture to it and go over some important aspects of generator design. These are synchronous generators we're talking about, and there's basically two types of those. There's the wound field type, and then there's a permanent magnet type, and the permanent magnet versions can be surface mounted or internal magnet machines. The wound field generators have been around a long time, and they're used in every jet engine flying in the world. They're the principal generators. They're wound field generators, and they use permanent magnet exciters to eliminate brushes and slip rings. So that's another aspect of this. One of the design of an exciter is a permanent magnet. It's a permanent magnet generator that's used on the same shaft of a wound field generator to eliminate the brushes, but that's really a permanent magnet generator in and of itself. But it has the added feature of being able to control the field for regulation for the wound field generator, which you can't do with the permanent magnet generator. You have limitations on the field control. So the top picture there is a picture of a wound field generator, and it consists of salient poles on the rotor that have coils wrapped around them. And those coils are powered with DC power, and it's transmitted either through a permanent magnet generator exciter, called an exciter, or there's slip rings on the shaft and brush rigging that connects the DC power. The bottom picture there shows the Toyota IPM for the Prius. It's not very common to use IPMs with a lot of saliency. It's not common to use those as permanent magnet generators because they don't make good generators. Their linearity is too poor. The reluctance torque, the reluctance aspect. It's better to have the magnets for a good permanent magnet generator. The best ones are the ones that are SPM, surface mounted. Okay, you can have some retainment from. You can have a sort of a quasi IPM as long as there's no saliency in it. It's a saliency that makes it hard to regulate. The synchronous generators, of course, are frequency dependent. The frequency of the voltage generated is a function of the speed. Here's a list at different frequencies of a list of speeds that you drive the generator at for different number of poles, and it tells you what resulting frequency you get. So if you want 400 hertz out of the generator, which is what you want on aircraft, they have 400 cycle AC. If you want 400 hertz AC with no converter to convert the rectify and regenerate the AC, then depending on the number of poles, either the speed you got to run it at to get that frequency. It's very seldom you ever use speed control of the prime mover, as I said in an earlier tutorial, that to regulate the voltage. Voltage is really regulated by rectifying the AC output of the PM generator and making DC out of that with a diode bridge and some smoothing capacitors. And then you regulate the DC output voltage what you want with a down chopper. Now you can use another inverter to generate sinusoidal voltages if that's what you need, and then you can have taps on there for different voltages, or you can have you can use a transformer with taps on the transformer. And an active regulated output uses a transistor rectifier, and you can boost the voltage for regulation. as I said before, the surface mount uh, generator is the best choice for linearity and minimum voltage drop under load. But many times for these kind of machines, if the magnets are mounted on the surface, they're going to require mechanical retention, such as a sleeve or wire wrap. Aircraft generators or aircraft exciters used as generators. Those have Inconel or stainless steel sleeves around the magnets. And some of them are single-phase machines, and some are three-phase. You don't, with the generator, you don't have to make it a three-phase machine. You can use a single-phase machine. Now, the IPMs are a good choice for short circuit fault protection, but still they have such a drop in voltage as a function of current that they're not linear, and it reduces the output power density. It says powder there. It's supposed to be power density. The configurations, the various configuration options are inside rotor with magnets configured as SPMs or IPM. Of course, we've talked about that. SPMs require retention, or outside rotor generators can be built in just like outside rotor motors with a rotor cup which retains itself. It's the rotor cup is self-retaining. This cup can be drawn or fabricated or cast, and it can be deep drawn out of thin material, and then to increase the yoke cross section is not uncommon to press a flux ring around the OD right in the center. Like you could deep draw a cup so that to put the magnets inside of, like a cut off end of a steel beer can, and you have that flange to mount it with, and excuse me, and the but the thickness of the yoke as a deep drawn cup probably isn't thick enough to carry the flux, so it's not uncommon to roll a piece of hot rolled steel and that's butted. It doesn't even have to be welded together. It can be butted, and that can be shrunk or pressed over the OD of the deep drawn cup. Axial flux configurations are possible also, and that's a very interesting concept for generators because even high-speed generators, you can retain the rotors of axial flux permanent magnet rotors. You retain those on the OD to keep them from flying apart with a sleeve around it. You can use alloy steel. You can use anything, because it doesn't matter if those retainment sleeves are magnetic, because they're not in the magnetic circuit. They're not across the face. So this is a very excellent way to make a high-speed generator. And you can have rotor stator rotor types, or stator rotor stator. In other words, two rotors with a stator in the middle, or two stators with a rotor in the middle. We saw pictures of those before. Now this is a common configuration of an aircraft type generator. It's similar to the Fanuc machines, and this is many of these are even single phase. They're not the aircraft exciters don't have to be three phase. They can be single phase. And this is there's two ways that you can arrange the magnets. Here you have the magnets arranged as normal surface magnets, and you get very low voltage droop with load. But for aircraft where fault tolerance is very important, they mount the magnets this way, like slabs here of like the samarium or the ceramic magnet motors. But in this case, you use rare earth magnets, and under normal operation, the flux linkage takes this path here. But as if you get a short in the windings, you'll get a very high short circuit current in the winding, so the MMF in the stator is very high, and so the flux will not take this path. It will go this way. So this is a path for the flux to go, and that reduces the flux linkage, and there's a balancing to take place so that the designs are very carefully initiated, such that at a certain sustainable short circuit current that won't cause this thing to burn or to to cause a fire and cause a plane to crash and the pilot get killed. That's carefully designed so that the voltage drop from the flux linkage drops as a function of a certain current that allows the short circuit current to be sustainable. And so this is really a field weakening that takes place. It's a high fault tolerant machine. This was developed by GE, by a research group up in Schenectady. To this day, aircraft generators are made this way. Here's some examples of some generators we're going to look at. The most famous one we're used to is the claw type alternator that's used for 12 volt in most every car in the world. This doesn't have magnets. It has a coil here with a claw type rotor and these pole pieces that look like this. This is the north, this is the south, 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 north, 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 north. You put these in here. So there's your poles across there. And then it has a three-phase winding in the stator. Now this has to have slip rings to get the DC current in this coil. So that coil sets up a field around here, and to close the circuit, it has to jump across from North Pole to South Pole there, and that's where the flux linkage comes from. That goes from these poles into the stator, and that's where the flux linkage comes from. And so as this rotates, this by the engine and a belt over the engine, driven by the engine, that will cause three-phase AC to come off of this machine. Now here's an example of an integral permanent magnet generator that's connected to a jet engine here. In this case, one of these impellers is a compressor that compresses the intake air, and then ignition is this is the compressor. Intake air comes in here, and then it passes over into this chamber, which there's ignition and fuel, and so that high pressure air combusts with the fuel and causes a very high pressure, and that drives this turbine, and there's the exhaust. So the compressor turbine is connected to the combustion turbine. So this compresses the air, and the air then burns with the fuel, and then the high pressure from that burning causes this to rotate. So it's a very nice system. Because of this fault tolerance problem, GE and Sunstrand developed switch reluctance generators for jet engines that would mount. This thing mounted right, they had the compressor blade down here and the combustion blade here, and this generator was mounted right in between the two. Instead of cantilevered off the end like this shows, it was mounted right in between. And this was because of the fault tolerance, because you get a short in the winding, since there's no magnet, why there's no short circuit current failure. So reluctance machines are aircraft popular for that. This is a case of a gearbox. This is a gearbox that's driven by some prime mover. This one happened to have been a jet engine, also a bigger one than that one. And it drove this gearbox, and there were actually two generators on this, a pair of generators. These are permanent magnet generators with their own bearings. And they're just like, these were surface mount machines, 4-pole machines, 120 kilowatts, 130 kilowatts at 1800 RPM. Oh, I'm sorry, this one is diesel powered. It wasn't, this one's diesel powered. It's not jet engine powered. Okay. So as we said, the two types are surface mounted. I keep repeating here, IPMs, but IPMs aren't used much for generators, except where fault tolerance is desirable. There's the axial flux machines are worthwhile to consider. Rotor stator type, then rotor stator rotor, and stator rotor stator. This is a stator rotor stator. See the magnets on the rotor. The power curve for a generator, particularly the ones this type here, this one here, the power curve for this type of machine looks like this. So here's the voltage and there's the output current, and the power is this curve here. So the peak power occurs there. The output voltage is a function of speed, and the output voltage drops. No, it's not. It's a function of speed, all right. But this is a curve here's the output power, but at high loads that will drop. So here's your constant power output at low speed. The phasor diagram and the lump parameter model are shown on this graph here, and here's all the parameters and the formula for the voltage generated. The gamma angle is the angle between the back EMF and the generated voltage. That's gamma angle. That's the load angle of a generator. This is the circuit diagram for a voltage regulation with diode rectifier. This generator can be a synchronous wound field generator or a PM generator. It doesn't really matter, but its output is rectified into DC, and then that DC regenerates AC voltages. This is a generator with just a plain diode, 6 diodes on it to drop the voltage, but you need capacitance across here to smooth it. But to regulate to some voltage lower than the rectified DC, to regulate to other voltage, you would use a DC chopper, use a transistor and turn it on and off, PWM. And this is the voltage and current equations for that. There's different load types that generators see. Of course, there's open circuit voltages, then there's short circuit currents, and then the infinite bus, which is like the grid. Then there's diode rectification with passive impedance and active rectifiers. For diode rectifier with a down chopper for voltage regulation is designed, you usually design the output to be 25 to 50% higher than the DC voltage you want to regulate. For active transistor rectification, it's the opposite. The back EMF is designed to be 25 to 50% lower than the regulated DC voltage to be regulated. And as we said before, the surface mount have very little voltage drop with load. IPMs have considerable voltage drop for load, and particularly they're designed that way on purpose. If the IPMs are made in a configuration like spokes in a wheel with a path on the ID, then they have good fault tolerance. Voltage regulation curves with lagging power factor would look something like this, and here's the power equation, the max and the rated power equation, and for a more rigorous discussion of PM performance connected with different load types, see Chapter 9 in our book there. Okay, that concludes this lecture. Thank you.